Okay, so we'll continue our discussion of the Kerr geometry. We talked about the black hole coordinates, so we could penetrate the horizon. There are some simple coordinate singularities that we should discuss before we talk about perhaps extending the Kerr geometry, and maybe a discussion is warranted as to what does that even mean, why bother extending the geometry. The first thing I want to discuss is the coordinate singularity along the symmetry axis. Symmetry axis, of course, is defined in Boyer-Lindquist coordinates by theta equals 0 and theta equals pi. So if you look at the metric, I'm not concerned about the time coordinate or the radial coordinate. It's usually these coordinate singularities happen in theta phi coordinate system. So if you look at the theta phi component of the Boyer-Lindquist metric, it reads like so. And we have an expression for G phi phi. A simple algebraic shuffle would actually verify that this is equal to rho squared times a very familiar object. Well, it's not that, obviously, because G phi phi is a very complicated object, but sine squared theta plus 1 plus, but the complication doesn't even affect us. It works out in a simple way. A squared sine to the 4th theta d phi squared. This is just algebraically easily verified. Now, in a Cartesian coordinate system, there's a dr component as well. So if you include the dr component, so if you look at this metric, this is nothing more than your familiar, right? So this combination just works beautifully. Again, the problem happens when you have the sine theta over here. So this literally translates to a nice Cartesian coordinates. This is not a problem at all. But you'll notice that this combination is also not a problem. For example, in a Cartesian coordinate system, sine squared theta d phi is nothing more than x dy minus y dx. Okay, so there exists a Cartesian version of Kerr geometry where the singularities just disappear. You can write the details of this is not very important, but the singularity, the seeming singularity with the sine squared theta going to 0 along the symmetry axis is pseudo. It's very coordinate independent. O'Neill has an exact expression, but he argues exactly the same way as well. This is a quick way of saying that there won't be a coordinate singularity. So when we talk about the Kerr geometry, regardless of Kerr's child coordinate system or the Boyer-Lindquist coordinate system, we'll just assume that it's well defined along the symmetry axis. If you need to, you can go to a Cartesian-like coordinate system where no singularity appears. Yeah, this is just a metric of a sphere, if you're confused, and that is not singular. Okay, that's the argument. We don't have this dr square over here, but the metric of a sphere is not singular. Okay, so we can include the symmetry axis. Now, interestingly enough, let me redraw this, the usual diagram that I draw. So in Kerr geometry, there is an r plus, and then there is an r minus, r minus, and just along the equatorial plane, which is theta over pi over 2, you get this ring singularity. Well, let me try to draw a 3D version of it. Yep, so this is r equals 0. R equals 0, theta equals pi over 2. But that's the only place there's a singularity. There's no singularity at r equals 0 for any other angle. This suggests that r equals 0 is not one point. It has a feature to it. So what we will do is construct, well, so remember the length of this is 2 pi a, where a is the angular momentum per unit mass of the Kerr geometry. So what we will do is consider an entire region of r equals 0, whatever shape it takes. Okay, and then, so here you are coming from r equals infinity along the axis or any axis, and then you reach r equals 0. There's no problem over there. Okay, so now what we'll do, because there's no problem over here, we'll extend the space-time to minus values of r. So now what we'll do is allow for r to go from minus infinity to infinity. As a matter of fact, O'Neill has a nice way of looking at this. He says the circle, a topological sphere perhaps, is, you draw this as, at any point here, you locate it as e to the r. So this entire region is a complete universe. You come all the way over here and you reach, in that scale diagram, r equals minus infinity. In doing so, you have broken the symmetry axis into two. This is r equals minus infinity. See, as r goes to minus infinity, this goes to 0. Yeah, this is sort of a schematic representation. So you have broken this axis into two axes. If you will, this is the north axis, this is the southern axis. They're not connected. So you fall down the northern axis, and then you go for an infinite long time till you reach this point. And that this point is not part of the manifold. Or if you're already here, you can choose to go this way. If you're here, you can choose to go this way by some time like Kerr. That's not a problem. But the point is, this line is not connected. This central point is not included. So now we have extended Kerr geometry both along the symmetry axis and to the negative values of r. Okay? It can be extended for any value except for when theta equals pi over 2. So just pause here, because then we're going to move in a different tangent. Any questions on this one? Any questions in terms of clarity?
So the bottom one is just defined as e to the r?
Yeah, it's e to the r, but theta equals pi.
Oh.
So this entire line, if you will, is theta equals 0 and theta equals pi. They're not connected. Yeah. So there are two poles in Kerr geometry. And you can compute the Riemann tensor over here. At r equals 0, you'll find that there's no any scalar curvature. Nothing blows up. You can do that over here. You can do that everywhere. It only blows up along the ring.
What is the coordinate of the point that is not a part of the manifold?
Oh, this is the point r equals minus infinity.
Twice.
Just like r equals infinity is not included. Yeah, and the curvature that you have to compute is nothing complicated. If you want any scalar curvature of Kerr geometry, either look it up or you enter it into Maple, you get an expression for Kretschmann scalar. It's the same Boyer-Lindquist coordinates that we're using, except theta is not equal to pi over 2. You will find that the Riemann curvature, and you extend it to the negative values of R, Riemann curvature is well defined. So this is not a hidden or a complicated argument. But there's an interesting point. So it looks like we have extended Kerr, and gosh, end of story, we have done everything. The symmetry axis is fine, and then we go beyond R equals 0 because there's no real singularity. We're extended it, we're done. Well, almost. There is a hidden problem here. If I look at an infalling geodesic in the Kerr-Child coordinate system, this is N that we talked about, this geodesic would come from infinitely far away, and it would just go beyond, cross the horizon, and go into the negative universe, and it'll stay there forever. It'll be future complete and past complete. It's going from R equals plus infinity, and it decreases all the way to R equals minus infinity, or it hits the singularity and it's done. Well, we expect that. So it's either it's either complete or it hits the ring singularity. Great, there's nothing much to be done here. But now, look at this outgoing, so this is our N, right? As a matter of fact, in Kerr-Child coordinate system, this is minus R bar. This is an easily integrable vector field. It just runs from minus infinity to infinity. Or it hits the R equals 0. But now remember the outgoing geodesic. The outgoing geodesic, close to the horizon, well, it can go on and it's future complete. It goes to R. As a matter of fact, this is L, and this is, I haven't talked about star coordinate system. Okay, so hold on. This is my L. Did we talk about the star coordinate system?
Both star and bar, I think.
Okay, well, I'll mention the important points of star. There's so many coordinate charts, I don't know if I've discussed all of that. But this guy would go forever. What we did talk about is which way L is future pointing in this region. L is not future pointing in this region. Whereas, what happens to L? On the horizon, L is tangent to the horizon. And in the interior region, minus L, so please note this, minus L is future pointing. We discussed this. It has to, because remember we said Kerr-Child is the black hole solution. You can't have L pointing as future pointing, because then it would come out of the horizon. So inside, between R plus and R minus, minus L is future pointing. And on the horizon, L is tangent to the horizon. This is in fact the null geodesic generator of the horizon. So if you look at L, if you look at the vector field L, this vector field, as it stands, prematurely ends as it reaches the horizon. You can't extend it smoothly backwards. L and minus L, they're two different vector fields. So if we consider this Kerr geometry, Kerr-Child geometry, where the event horizon has no singularities, this outgoing light beam presumably just stops existing at the event horizon where nothing is going bad. That means this geometry is not complete. Our goal would be to construct a maximal extension of Kerr geometry so that at least geodesics, affinely parameterized geodesics, are either complete or they die at the singularity. You know, be it an immortal observer or a beam of light, you don't want to suddenly stop existing in a region of space-time where nothing goes wrong. That is the premise of all of that. Now, maximal Kerr geometry is rather cumbersome, but it's not difficult. So there are different patches, if you're familiar with this, there are different patches you add, and you get a nice Penrose tiles, as they're called. As a matter of fact, these are infinite patches that you can add. So what I'll do is I'll construct one patch in great detail. So you may be bored in part of the discussion because largely the argument is just algebra or calculus 1. But we'll just painstakingly do it so that it becomes clear. And then at the end of it all, everything we have learned will be captured with one diagram. And then the Penrose tiles is just a stack up of two versions of those diagrams. And the two versions of the diagrams are very similar. So there's no complication here except keeping track of everything, and it's mostly algebra and calculus. And forgive me, I'm just going to do all of it so that there's no mystery. Okay? All right. Again, our goal is so that this guy doesn't just stop existing for no reason. Remember, this is not a problematic surface. So as the arguments will be the essential content of O'Neill's book. I use slightly different notation, and I'm not as elaborate in sort of the generalized geometric discussions, but rather I'm very concrete and apparent. So you'll have a dense set of information that is contained in that book in just a couple of lectures. There are some important calculations to be done. So a bit tedious, but let me begin with tedium. Yeah. So first of all, let me set up a little bit of notation. I have written this multiple times before, but it doesn't hurt to write it. So T bar, for example, is T plus T of R, and this T of R is nothing more than integral of R squared plus A squared over delta dr. But you know what? It doesn't hurt to write one more time. Just so you have it. Okay, and similarly, so more importantly, note that as R approaches R plus and R minus, T approaches minus and plus infinity. We have to do that. We have to do a singular transformation to get rid of a singular surface, or coordinate singularity. And also we had phi bar equals phi plus A of R, and this A of R is nothing more than A over delta dr. This is a slightly smaller integral, A over R plus minus R minus natural log The first observation I'll make is this important result, A of R minus A over R plus minus squared. I don't know if the recording is very clear, so as I write it, I'm going to read it out. It's A over R plus minus squared plus A squared plus T of R. But you have these two expressions right here, and when I insert it, I'll get the following. Let me continue here, so I can write it a little big. Minus A over R plus minus squared plus A squared R plus minus plus R minus plus natural log r minus, this is a mouthful, r minus plus, but this is just really inserting these two expressions. That's what you'll find. So you will notice the following. If I look at the plus combination, a minus a over r plus squared. So I'm picking the upper subscript, r plus squared plus a squared t. I'll find that. So when I put the upper subscript, I have r minus r minus. So this is analytic at r equals r plus. This one only has a problem at r minus. Yep. And the other combination, r minus squared plus a squared t is analytic r minus. Yeah. So remember, just looking at this function, it could possibly have a problem only when the argument of the natural log goes to 0, or infinity, of course, but that's not included in our space-time. So for when I pick the plus, the upper subscript here, I'm getting r minus over here. So at r equals r plus, nothing goes wrong. So it's a nice, so while these guys have certain singularities, this is a nice combination at r equals r plus. So that is just one fact that we have. So what I will do, I can leave that there for a while. I'm going to do the following. I'm going to break down the discussion of the creation of a new patch and just talk about a small chunk. So I'm going to take, so we had k bar coordinate system. I had forgotten if I talked about k star. If I've talked about it, great, but I'll talk about it as needed along the way. So for the moment, everything is bar. So I'm going to talk about one bar, and this is, of course, in the bar coordinate system. And I'm going to define a coordinate chart, a new coordinate chart on these two parts. When I say block 1, what do I mean? R greater than R plus. So by this, I mean, let me clarify here. I might have to erase this. 1 is r greater than r plus, 2 is r minus, r plus, and 3, which we won't see 3 today, is r less than r minus. And when I put a bar on top of that, it just means this exact same region in the Kerr's child coordinate system. Okay? So I'm going to put a new chart on this. That is my goal. So I'm going to define u plus to be equal to the exponential of minus kappa plus. I have to tell you what that is. It's a constant. And so I do use my star coordinate system. Fine, I'll have to explain this. And v plus to be equal to exp k plus t bar. And over here, u plus is minus exp minus k plus t star, and another function v plus equal to exp k plus t bar. You already know the bar coordinate system. I have to talk about the star coordinate system, but before that, but that's only two coordinate systems. These two you will soon see will replace t and r. But you know theta. Theta is very harmless. We just talked about the theta equals 0 not being a problem, theta equals pi over 2 not being a problem. Theta is never a problem in this. But turns out we'll have to change the phi coordinate system. So I'm going to define phi plus. So we have this plus coordinate system on the two blocks of Kerr geometry. We have to show that it's a valid coordinate system, of course. Phi bar plus phi star minus a over r plus squared plus a squared t bar plus t star. There's a constant mentioned over here, kappa. I talked about kappa plus, but very soon there's going to be a kappa minus, so I might as well define both of them. That is nothing more than r. So again, so that you can hear it on the recording if you can see it properly, I have kappa plus minus, that is equal to r plus minus r minus plus divided by 2r plus, and I'm glad I'm saying that because it's even hard to read at the bottom of the board here, but this is 2 times r plus minus that quantity squared plus a squared. Okay, so these are the definitions. I have to tell you what the star coordinates are.
The expression for phi plus p?
I think so. Sorry, yeah, I didn't. Yeah, it's just a bracket. Sorry, thank you. Yeah.
What do you mean when you say we have to show that this is a valid coordinate system? You're just checking for singularities?
Checking for singularities, and also I don't recall talking about Kerr as our K star. Yeah. So why K bar is the black hole coordinate system? Why is the K bar black hole coordinate system? Well, because in the bar coordinate system, for one thing, this is just well defined everywhere, and that's defined to be future pointing. So it's the bar coordinate is well defined through the horizon, and n is minus of the partial derivative with respect to r bar, and it's just integrable through and through. We declare that minus ddr is future pointing, meaning even through the horizon, at the horizon, and through the horizon, in falling is future pointing. So that's what makes it black hole. It just pulls you in. There's no getting out. As I mentioned, in block 2, because of that, if this is to be future pointing, I think we discussed this, minus L is future pointing. You cannot have a light beam coming out of the event horizon in the black hole spacetime. So close to a bar spacetime is the star spacetime. So here I have T star equals T minus T over R, phi star equals phi minus A of R. So all that has happened is the pluses have become minus, and R star is equal to R, and theta star is equal to theta. What happens in this is that now L is equal to this in this coordinate system. And therefore, we declare in the star spacetime, meaning in block 1 star, 2 star, and 3 star. We declare that this guy, L, is future pointing null. So DDR star is future pointing null. And so the outgoing light beam just goes through. This is the white hole geometry. And you will see that T star is equal to T minus uppercase T, which is equal to T star, what is that? Plus T, I wonder if I got the plus and minus wrong. Let me take a look at this. I don't think I have it with me. Do you have notes from before? Did I? How did I define? I'm not sure how I defined this. T star. Yeah. So let me do it this way. T star equals T, but T is T bar minus T. Yeah, I think I defined it correctly, thankfully. So what am I doing here? T star equals T minus T of R, but T is T bar minus T, correct? T bar equals T plus T. So I'm replacing T with T bar minus T. And so I get T bar minus 2T. And so these coordinates are invertible. And same thing with phi star. So there's a simple relationship between. So just like the Kerr-Child, the K bar, or the Kerr bar coordinate system is well defined through the horizon, the Kerr star coordinate system is well defined through the horizon. In the Kerr bar coordinate system, it is the infalling geodesic, null geodesic, that is future pointing everywhere. In the Kerr star coordinate system, it's the outgoing null geodesic that is future pointing everywhere. And there's a simple algebraic relationship between the two. And it is a mix match of star coordinate system and bar coordinate system that defines this patch. I have to show that all of this is meaningful. It's just easy to write down functions. Any questions thus far?
What are the requirements for these functions where the patches meet?
So at the moment, we don't, you mean where block 1 and block, so they meet at R plus? Yes, we have to show a nice transition function. Again, all of this will be explicitly shown. Just because of a lack of space, this is something you want to either commit to memory or write it down somewhere so that as I talk, okay? All right, so slow but steady, but we'll do every single calculation. So first of all, what I want to do is, claim rather, the functions u plus, v plus, theta plus, phi plus is, I guess, collectively well defined. In blocks 1 bar, 2 bar, and R plus. Because adjoining 1 bar and 2 bar is R plus. Okay, so first part, V plus is equal to EXP kappa plus T bar. T bar is well defined over, and it's bar, right? So let me do this. R bar equals R plus. T bar is well defined in the bar coordinate system. So is well defined. Rather. So this is 1 bar and 2 bar, which means all the bar coordinates are well defined. By definition, T bar, R bar, theta bar, phi bar are well defined. We need to show that the others are well defined. So I never have to worry about these two. I don't have to worry about theta. I need to show that these guys are well. This is well defined, for example, because this doesn't affect anything, and this one is well defined. I'm going to show this one first because that's why we had that nice relationship ahead of time. So let me, so second point here is if I look at phi plus, and what I'm going to do is replace phi star and T star with phi bar and T bar. And when I do, I get this to be equal to phi bar minus A over R plus squared plus A squared. Again, I'm reading this out because of all the subscript. Phi plus is equal to phi bar minus A over R plus squared plus A squared T bar minus A minus A over R plus squared plus A squared T. Guess what was the first result we just showed about this combination? This is the one with plus. This is well defined across and phi bar and T bar is well defined. So what did I do? I replaced this phi star with phi bar minus 2. Oh, I just recalled, previously when I wrote, I said this is equal to phi minus T. With phi, it should have been A. Just note, this is the T star equals T minus T. Yep, so please correct your notes. That's the definition. So also phi star, that becomes phi bar minus 2A. That's the correction. I wrote 2T, and T star is equal to T bar minus 2T. Okay?
Is R equals R minus included in block 2?
No. Block 2, the boundary of block 2. Block 1 and block 2 are open edges. Block 1 is R greater than R plus. Block 2 is R greater than R minus and less than R plus. Block 3 is R less than R minus. So that is why I'm saying this function is well defined at the two open blocks and at R bar equals R plus. So that it'll be well defined in the Kerr bar coordinate system when R is greater than R minus, which includes R plus. Yes?
So which block includes R equals R minus?
Blocks don't. But when you combine all of them, it has to include the...
So these blocks aren't dividing the manifold?
No. It doesn't include R plus and R minus, and that is why I said I'm including that in particular. So V is well defined, phi plus is well defined, obviously theta plus is well defined. What's the only thing left to show? U. Because these expressions are there, so I know I made a correction from a few minutes ago. The very important, this A, please do note. Any questions that I can clarify? So whenever you see T and T bar and T star, it goes with uppercase T. Whenever you see phi, it goes with A. And it's this combination that's well defined. This is bar coordinate system, which is already defined, well defined in the bar geometry. So it remains to show that U plus can be fixed. Since I call these points 1 and 2, I'm going to call the last one 3. So what am I trying to do here? So point 3. First of all, note that this is sine sine of R minus R plus e to the minus kappa plus T bar e xp 2 kappa plus the sine. Oh, this is the sine of this quantity, huh? SGN would have been better, but I don't feel like conserving one letter. So this SGN or SIGN is just supposed to handle this plus and minus. So when R is greater than R plus, it is plus. So in block 1, it is positive. When R is between R minus and R plus, this is negative, and that's that negative. Then, what did I do? I don't know about T star, but I know T bar is well defined. So I write T star in terms of T bar. And T star is T bar minus 2 times that uppercase T. So I have this, and I have that. Yeah? Okay. And so I wrote the expression for T. It had a couple of natural logs in it. I'm going to erase it, exponentiate the natural logs, so I'm going to get a couple of absolute value functions. So I'm going to write this again as, it is SGN, well, it doesn't matter. R minus R plus, I'm just copying these guys down. This is not very harmful, but we have to make sure it transitions smoothly. But this is totally safe. EXP minus K plus T bar. Now, I have this exponential function. This T had 3 terms. The first term was just R. The second term was natural log of R minus R plus, and the third term was natural log of R minus R minus. So you will get 3 terms, the first of which is just R. So again, I'm just going to do EXP 2 kappa plus R. Then the 2 natural log terms. So then I would have R minus R plus, and then R minus R minus. You can verify this part, just taking the natural log of T. This is what it comes out to be. You might wonder where the coefficients went. It went because of this kappa plus is designed to take care of the coefficients of T. So this becomes a reasonably nice expression. But note the following. SIGN of R minus R plus Let me continue with my notation. Times r minus r plus. This is nothing more than r minus r plus. This is always positive, but when r is greater than r plus, this is 1. This is precisely that. When r is less than r plus, it's minus, but this is also minus, so it's that. Therefore, I'm going to erase the harmless part and write u plus is equal to, in this patch, I have this is equal to r minus r plus, r minus r minus to the minus r minus over r plus, and this is a smooth function at r equals r plus. T bar is well defined. That doesn't mean that this is a coordinate system. It just says these four are analytic functions when r is greater than r minus. For us to show that in fact they form a nice coordinate system, I must take the Jacobian of this map and show that its determinant is not 0. We will do that. Like I said, we'll just one sample calculation will be done in great detail. But before I proceed, I would like to know, how are we doing on time?
We're at 47 minutes.
Should we stop this here? And yeah. So my goal when we return would be to show that these well-defined functions in fact form a coordinate system when r is greater than r minus, so that it includes the r plus.